All right, so 6.4, which is the central limit theorem. 6.4 central limit theorem, which allows us to find probabilities of means. And we know from the previous section its distribution is normal, and the mean of the means is equal to the mean. So the mean of the sample means is equal to the probability to the mean of the population. And that's basically what we're using. So really, the central limit theorem comes like this. It says that the mean of the sample means is equal to the mean of the population. But then the standard deviation of all the sample means, it's not quite equal to the standard deviation of the population, but it's actually equal to the standard deviation of the population divided by the square root of the sample size. So that means that it allows us to find z-scores. Now we know z-score for just like an individual x is equal to x minus mu all over sigma. But if I want to find, say, the z-score for x bar, so the z-score for these means, you know, it's going to be, this is your x value minus the mean of those divided by the standard deviation of those, and each one of these are calculated here. So really I can say the mean of x bar is equal to, you know, that x bar minus, well, the mean of the sample means is equal to the mean of the population, and the standard deviation of the sample means is equal to the standard, the standard deviation divided by the square root of n. Now be careful when you guys are calculating these things on your calculator. You really have to force parentheses here and parentheses here. If you don't put them in, you're going to get something off a little bit, okay? So we're going to be using that idea. So you asked questions on number 2. Number 2 says, weights of golden retriever dogs are normally distributed. Samples, weights of golden retriever dogs, each of size n equals 15, are randomly collected, and the sample means are found. Is it correct to conclude that the sample means cannot be treated as being from a normal distribution because the sample size is too small? Explain. Well, this theorem actually had some restrictions on it. You can use this 2 different ways. Like, one restriction is if x bar comes from like a normal distribution. Comes from a normal distribution, then all your x bars will also have a normal distribution. Then there's no restriction on size n. The other case is if these x bars come from a distribution that might not be normal, like a uniform distribution or U-shaped distribution or whatever shape distribution, then n has to be bigger than 30. So it comes from a non-normal distribution. Then this is only true if n is greater than 30. Then that, if n is greater than 30. Is that clear? So if the original population has a normal distribution, it doesn't matter the size of n. But if it comes from something that's not normal, then n has to be bigger than 30. So let's read the question again. So it says weights of golden retriever dogs have a normal distribution. You guys agree? So since the population has a normal distribution, does n matter? Does the size of n matter? No. Nope. The distribution of the sample means will always be normal regardless of the size of n. So the question asks, can it be treated as normal? So yes, it is normal. I should say is a normal distribution. What I mean by that is the distribution of the sample means, because the population that we're sampling from is normal. So I guess since we're doing a video, we'll kind of discuss what this means again. So bear with me, we're going to do that picture again that we did last class. So say this is our population. So if our population has a normal distribution, these are just a bunch of data points, and we know if we line all the data points up, what you're going to see that bell-shaped curve, right? Populations could also have a uniform distribution, so something that might look like this. So all these, equally as likely, right? And then the other one that I showed you was a U-shape, yeah. There are other shapes. You guys are like, there are other shapes, but these are like two that we tend to look at. So uniform. This has normal. This is uniform. And this is U-shaped. What happens is when we start taking sample means from here, what I mean by that is I'm going to say, like, this represents a bunch of dots, okay? So what I'm going to do is I'm going to take samples of size n, and I'm going to take the means of those particular samples, and I'm going to plot those means themselves. So these are going to be sample means down here. These are going to be sample means. So if n is equal to, say, 10, what you'll notice is that if it's a normal distribution, the sample means will also have a normal distribution. Now I did try to draw this a little skinnier. See how this looks a little wider, so it has more variation. Standard deviation is a little bigger. Notice the standard deviation is a little smaller. The reason why is because if you look at the standard deviation of the sample means is the original standard deviation divided by the square root of 10. So since the square root of 10 is, I don't know, it's probably somewhere around 3-ish, right? So if I take a number and divide it by 3, you guys agree that the standard deviation is getting smaller? If the standard deviation gets smaller, this thing is going to squish a little bit. And if I have like n is equal to 30, now I'm divided by a number that's like around 5, right? So it's going to get even skinnier. So it's going to look even skinnier. But it's still going to have a bell shape. So if the population is normal, all the sample means are normal. But when it comes to like a uniform distribution, when n equals 10, it's going to start showing kind of like a bell shape. But I wouldn't say that's quite normal yet, okay? But as n gets closer to 30, maybe I should say even 40. Because if it's bigger than 30, that actually really starts looking normal. Like that, like this thing really starts to look like a bell-shaped curve. It starts to take shape. So what's interesting is the distribution of the sample means is always going to be normal regardless of the original population. As long as n is bigger than 30, it'll actually kind of normalize. It's really cool. So what's kind of interesting about this is, remember, when we find probabilities, we use this z-chart table, right? And the z-chart table only works for bell-shaped curves. What's interesting is, again, regardless of the original population distribution, you can normalize it with a bunch of sample means. Even this it's kind of a similar thing. I don't know. I don't really know what it's going to look like. But I know as n gets closer to 30, bigger than 30, what you're going to get is you're going to get a bell-shaped curve. So these things will eventually kind of normalize. So these you can use the z-scores, right? So what the question was asking is, question 2 says the distribution of dogs' weights, they're already normal, right? So even if I take size 10 or size 40, it doesn't matter. They're all normal, right? Because if the population is normal, they're all normal. But if I'm talking about random digits on a phone, it's not normal. It's going to be some uniform distribution, right? So if I have digits between 0 and 9, what's the probability of you picking a 1? Well, it's going to be 1 out of 10, right? So no matter what number I pick for probabilities, the probability of getting a 2 is 1 out of 10. So you're going to see that uniform distribution. But if I take a bunch of samples and I take their means, it's weird that as n gets closer to 40, if I keep doing that uniform distribution is going to bell shape. Okay. Number 4. Coffee's kicking in. Annual incomes are known to have a distribution that is skewed to the right instead of being normally distributed. Assume that we collect a large n greater than 30 random sample of annual incomes. Can the distribution of the incomes in that sample be approximated by a normal distribution because the sample size is large? That's a good question. Oh, I see what they're asking. I got it now. They're not taking sample means, they're just taking samples. Is that clear? Like they're not taking samples and then taking the mean of the sample. They're just taking a bunch of samples out of there and they're asking what the distribution of the samples are. Well, if you take a sufficiently large, so what they have for number 4 is we know that income has a skewed right curve because some people are just stupid rich, right? So we'll never get there, right? Like billions and billions of dollars rich is insane. So, they have most of us. Let's see what's up. So what they mean by a skewed right is it looks like that, right? And to be honest, it's way skewed right. Like this thing like goes off to the wall. Actually it goes like a block that way if you really want to understand that. Is that clear how skewed right it is? Okay, so this is going to be like essentially the income that you'd expect to be like most people, right? But technically, if you find the mean of this, if I tried to find the mean of this, the mean is actually not going to land here because this is going to pull the mean off to the right. So the mean is actually going to be somewhere way over here, especially how pulled right it is. It's probably going to be way over here. So if you calculate the mean of our income, we're going to look like super rich. Is that kind of clear? That $13 billion that whatever the owner of Amazon makes is going to pull our mean way over. So it's nice. I wish we all had a mean of what it'd probably be close to like $1 million, right? If we took our mean. I don't know. I'm just guessing. But if I bet you if we took the mean, it'd probably be $1 million or more. So a mean is not a good one because the mean is going to be way out here. So what we do is we tend to take the median of this, right? And the median is going to send us more about right here. So it's going to kind of take care of Bezos and pulling our mean all the way to the right. So all right. What they say is we have a whole bunch of distribution points in here, right? Now, if I just grab a sample from this, only a sample, I'm just going to grab a huge sample. Does it make sense that the sample itself is also going to be skewed? If I grab a huge sample? The difference is if you take a bunch of samples and then calculate their means, the sample means will end up being normally distributed, but not the sample itself. Is that clear? So remember when we're calculating, we're actually calculating calculating z-scores of sample means as opposed to just z-scores of x, right? Is that clear? What's going to be kind of nice is we'll be able to work with that. This curve actually shows itself. It's called kind of the chi-squared curve. We'll see a little bit later. So since I'm only bringing out a sample and I'm not taking the sample means, then a very large sample is still going to have a skewed right. Is that clear? If I just grab a bunch of these dots, they're going to plot like this, aren't they? Okay. All right, number 17. All right, redesign of ejection seats. This is when the women were finally allowed to become pilots of fighter jets. Engineers needed to redesign the ejection seats because they had been originally designed for men only. The ACES-2 ejection seats were designed for men weighing between 140 and 211 pounds. Weights of women are now normally distributed with a mean of, what do they mean by now? Whatever, I'm just saying, women have a normal distribution, so they're normally distributed with a mean of 171 pounds and a standard deviation of 46. Oh, they must be now, like, as opposed to back then when everybody was a little lighter. So, this is kind of the way I'm going to ask it on a test. I'm going to give you something very similar to this. Like, A is going to be for the individual, B is going to be for the group, for the sample means, and then C is going to ask what one's more relevant, okay? Sometimes the individual is more relevant, sometimes the group is more relevant. Is that clear? Let's think about this ejection seat before I ask like group or individual. In this case, do I care more about the individual or do I care more about the group? How many people are flying a jet at one time? Is it a group of women or is it a single woman? Does that make sense that in this case it should be the individual that's more? Okay. Now if I'm talking about a plane loaded with people, then I care more about the sample means, the group of people, as opposed to the individual. Is that clear? It depends on what we're doing. Are we doing it to a group of people or are we doing it just to an individual? All right, so It says for A, it says if one woman is randomly selected, find the probability that her weight is between 140 and 211 pounds. So really, letter A is just a question right out of 6.2. Is that clear? 6.2 asks you to find the probability given an X value. Okay. So number 17. What I know is that the mean of women, they said, is 171 pounds. And the standard deviation is 46 pounds. So what they're asking us is they want to find the probability that that this woman is between 140 and 211 pounds. They basically want to know if that seat's going to work. Is that clear? If it's going to fit most women? Because that what they said is I think the ejection seat is rated for that, right? It's rated between 140 and 211 pounds. That's what that new seat is rated for. So let's see if we get most women. Because that's kind of the goal, right? We don't want to exclude them if we want fighter pilots, we need to make sure they all fit in there, right? All right, so that means I'm going to have to, what do I have to do first? That's correct. Yeah, I have to turn this into a z-score. What I know is this is going to be the probability that z is between, well, I don't know, right? How do you find those values? Well, you have to figure out those as far as the z-score. So the z-score of 140 is going to be equal to, remember z-score is x minus mu over sigma, right?
Yes.
So x is going to be 140 minus 171 all over 46. So this is equal to, it's funny, you guys remember finding z-scores? It's like chapter 1. And now that's basically all we do. All right, so clear. 140 minus 171. Cool. So negative 0.67. So remember, z-scores we round to the hundredths place. The only reason why is because our table's to the hundredths place, right? Okay. And then z for 211 is going to be equal to 211 minus 171 all over 46. You guys have that one too? Positive what?
0.87.
What is it?
0.87.
0.87? That's not great. 0.87? Huh. I was kind of hoping that it would be more inclusive. Yeah.
It is.
Well, it's not bad. Remember, to be like 95%, you'd have to be in between plus or minus 2, right?
Yes.
This is kind of between plus or minus 1. Is that kind of clear?
Mm-hmm.
I don't know. Maybe the population of fighter jet pilots tends to be trimmer than the population. Is that kind of clear? Like, you know, these people, these military people, whether it be men or women, are definitely more fit than me.
Yes, they are.
Hey!
They're more fit than me as well.
Yeah, that's true. Okay, so the probability that 140 is less than x is less than 211 is equal to the probability that minus 0.67 is less than z, which is less than 0.87. Now, how do you find the probability between? What do you got to do?
We gotta subtract the least scores.
Yeah, careful. Do I subtract the z-scores or do I subtract the areas?
With the areas.
There we go. So I have to subtract the areas. So z less than 0.87, the bigger area, because it's the bigger z-score, right?
Yep.
Minus the probability of z less than negative 0.67. It is a very common mistake to try to subtract those two numbers, right? You don't want to subtract the z-scores. You need to find the area first and subtract the area. Is that clear? Okay, so let's find those z-scores. So 0.87.
27 is 0.807.
And then minus
2515.
25 what?
1.4.
1.4. Fantastic. Okay, so when we subtract these things, 8078 minus 2514, I get 50. So 0.5564. Okay, well, is that inclusive? Well, I guess they're not really asking, but I'm gonna ask you. Is that pretty inclusive? What percentage is that?
It's above 5.
55.
Yeah, 55.64%. I don't know. It's over half the women. I guess the majority of women can use it. You guys agree? Okay. I don't know. It's hoping for more. Whatever, designers. Okay, so V. But again, they might be more fit than us, so maybe that actually is 95% of military people. I don't know. Okay, so B is asking for if 25 different women are randomly selected, find the probability that their mean weight is between this. So in this case, what they're asking is more about the group, right? So the way we find z-scores for your means of a group is going to be using this thing, right? Is that clear? Okay, so what they're asking for is what's the probability that 140 is less than x bar, which is less than 211. Is that clear? Remember the difference between finding the z-score of x and finding the z-score of x bars. It's ever so slight, but when you want to find the z-score for x bars, it's going to be equal to whatever that x bar is, the values that they're giving us, minus the mean all over the standard deviation divided by the square root of n. And again, the only real difference here is, the 140 and the 211 are still going to go there in this case because that's what they're asking here. Is that clear? But instead of just being 46 on the bottom, it's going to be 46 divided by the square root of what? How big is the people? How many women? 25. Okay, so that means this z-score for a 140 is going to be equal to 140 minus 171 divided by 46 divided by the square root of 25. Oh, thank you so much. So you're welcome to just write 5 in the bottom if it's a perfect square. I'm cool with that. And then the z-score for 211 is going to be equal to 211 minus 171 divided by 46, square root of 25. And then again, don't forget put parentheses around these things when you try to do them. That's not right.
Negative 3.3.
That's what you got? Cool. So this is negative 3.37. And then the other one, this is kind of a cool trick. If you have some kind of complicated expression here, you can hit second and enter, and what it'll do is it'll put the entire thing back in there. And then you can just go over and change the number that you care about. So instead of 140, I want 211. Right? And then just pop enter. Wow, this is really inclusive when it comes to a group, right? 5. Wow. Okay, so that one's off the chart, right? That one's almost off the chart. Remember, anything below negative 3.5 and above 3.5 is going to be, your 0.001, and then your 0.9999. So, all right. So that means the probability that 140 is less than x bar, which is less than 211, is going to be equal to the probability that your minus 3.37 is less than z, which is less than 4.35. And the way you find probabilities is you have to subtract the area to the left of 4.35, and then you have to subtract, it's bigger minus smaller, let's just go with that. So z less than negative 3.37. So this one right here is 0.9999, right? Because anything above 3.5, and you can kind of see it right here, so it says anything above 3.5 is just this number. Now the negative 3.37 is, you guys get 0.0004?
Yes.
So minus 0.0004, so 0.9995. That's a lot. Okay, so that's really inclusive if I'm talking about a group of 25, but I think C asks what's more useful, right? So when redesigning the fighter jet ejection seat to better accommodate women, which probability is more relevant? The one from A or the one from B?
From A.
Yeah, because I'm not putting 25 women in that seat. You guys agree? At one time? You're only putting an individual in that seat. So part A is more useful. Hopefully the next question, we really went through the time today. Okay, hopefully the next question is, so A is better because it's the individuals who's sitting there. 19. All right, so Boeing, I don't know if I'm going to go through this, but I want to kind of talk about this. That's still the same, though. I was kind of hoping that, we're not going to go through this because it's the exact same thing that we just did. So what it says is it gives us, it says a whole 200 passengers and doors have a, it says Boeing 757 carries 200 passengers and has doors with a height of 72 inches. Heights of men have a normal distribution with a mean of 68.6 and a standard deviation of 2.8. So A asks if a male passenger is selected, find the probability he can fit through that door. So A is just like the A we did before. Just find the z-score like we did in 6.2. B says is if half of the 200 passengers are men, find the probability that the mean height of 100 men is less than 72 inches. So what they're asking for in part B is they're asking, it's the same thing as we did in B, except you have the square root of 100 on the bottom of the standard deviation. Is that clear? Now they're asking for left, so it's just area to the left, it's not area between. So this is, honestly, it's an easier problem because I have to find only one z-score as opposed to two. When considering comfort and safety of passenger, which result is more relevant? Yeah, it says A, but man, I think they're, yeah, because it would be part A because you're only putting one through at a time, right? Does that make sense? Like A would be more relevant because how many people are walking through at a time? Yeah. Now, if you're asking for like weight capacity of an airplane, does it make sense that you care about the weight as a whole? So, like, if you're considering weight capacity, question A, which asks for the individual, is not quite as important as question B, which asks for the group. Okay. So you kind of have to ask, what's happening at this moment in time? Do we care about the group of people, or do we care about the individual? So in this case, only one person is going through at a time. Now, why do they build heights for men as opposed for women?
Men tend to be bigger than women.
That's right, yep, because if you can accommodate most of the men, then you immediately accommodate almost all the women, right? So that's why. All right.